Okay, for this part, we're looking into the introduction to non-homogeneous differential equations. And just as a rule of thumb, what separates non-homogeneous from homogeneous differential equations is that for homogeneous differential equations, those equations can be set equal to zero, whereas the non-homogeneous equations, if we were to take the terms in the dependent variable, we could not set the equation equal to zero. So homogeneous means, in essence, set equal to zero. Non-homogeneous, we have not set equal to zero. And in non-homogeneous differential equations, okay, we have the solution y of x will be comprised of two portions, and we have set equal to y sub c of x, and this is what is referred to as the complementary solution. And that would have been the entire solution if we had the equation to be homogeneous. And for the second portion, that is going to be the particular solution. And you can regard that as like an abridged form of the whole y of x in a non-homogeneous differential equation. And let me just kind of give you a backdrop, okay, to what we have, sort of making a transition from homogeneous to non-homogeneous equations. And I'm just going to keep things along the lines of working with a homogeneous equation to start out with. Okay, like if you have like a first order homogeneous differential equation, okay, and we'll say that we have like in terms of solving for y. And we say that we have y prime is equal to 0. Okay, so you have y prime is equal to 0. And now for what we have here for y prime is equal to 0. Okay, if I put this in terms of a characteristic root equation, well, you got a first order derivative in y, and if I put this in algebraic context for a characteristic root equation, we have the first order of r is equal to 0, so there is only one root, and that is going to be equal to 0. And so for what we will have for this solution, we're going to have that y of x is equal to a constant. Okay, now let's say that for a non-homogeneous equation, and I'll start out with perhaps the most basic one, and we'll say that we have y prime is equal to e to the x. Okay. And again, okay, now for what is regarded as the complementary solution, so I'm just going to repeat this part. Okay, so if you have like the complementary part, okay, so you have like y prime is equal to 0, and you have also your characteristic root is going to be solely at 0, and where we have y of x equal to c sub 1, okay, for y prime is equal to e to the x, that's going to be referred to as the complementary portion of what we have in the solution of y prime is equal to e raised to the x. So you have y sub c of x is equal to the constant. Now, with e to the x prevents this equation from becoming homogeneous. And for what we have in the case of e to the x, what we're going to do here is using this guideline here and setting up like a family of derivatives. Okay, so if you notice, you have like with e to the x, that's going to be in the family of the function defined by e raised to the a times x. And you had the family of derivatives and all that, like have e to the ax, and within the family have just e to the ax, and that is going to be like if you have like e to the 2x, you have like e to the 2x, 2e to the 2x, 4e to the 2x, and the diminutive form is just going to end up being like a multiple of e to the 2x. So we're not worried about multiples. So we have for e to the x, Okay, the derivative of e to the x is going to be just e to the x itself. And there's no constant, okay, that is derived from e to the x. And so for what we have here, we can set up a particular solution with a coefficient a to solve for. And we say that we have for y sub p, we can say that is equal to a times e to the x. And if I take the derivative of this, well, guess what? I'm going to have y sub p prime is equal to a times e to the x. And guess what? I already have established that y prime is equal to e to the x. And if I put that statement in terms of y sub p prime is equal to e to the x, well, guess what? I had the same statement with y sub p prime. Okay, it got simultaneously at a e to the x, and also from the original equation I have equal to e to the x. So if I'm looking at solving for a, I can say that I have a e to the x is equal to e to the x. And guess what? A is going to be equal to 1. And with the value of a determined to be at 1, it's going to turn out that for y sub p is just going to be 1 e to the x, or just simply e to the x. And looking at solving for y of x, again, we're looking at adding together the complementary and the particular portions in the solution to get all of y of x. Okay, so for what we have clustering together, okay, so we have y of x is going to be equal to y sub c of x plus y sub p of x. It can also be the other way around. And that is going to be equal to e to the x plus the constant c sub 1. And let's say if I go with an individual term and say that we have, looking at solving for x, whereupon we have that y prime is equal to, we'll say 3 times the sine of 2x. Now again, if I had y prime equal to 0, again, I would have the complementary solution to be where we have y sub c of x is equal to the constant. Now, for 3 times the sine of 2x, now again, I have the variable factor portion. We had the sine of 2x. And if I put this in the context of a reduced family of derivatives, now going back, okay, now for the sine of 2x, that is a form of the sine of ax. And for the family of derivatives, you have like the sine of ax, the derivative of sine goes to cosine. Now the derivative of cosine will go to negative sine, and that of negative sine will go to negative cosine. But we're not interested in the sine values or the multiples. We're interested in just like the diminutive form, like, you know, like sine of x and cosine of x. They were going to be going back and forth. Okay, even though the signs may change, even though the coefficients may change, but for what we have specifically in the case of the sine of 2x, you're going to have within the family. Okay, so you got the term, you got the sine of 2x, and the derivative of the sine of 2x is going to go to a multiple of the cosine of 2x. And there's nothing in the set, okay, that we had to reduce to a constant. Okay, and I'll mention something about duplication, but we don't have this particular scenario right yet. Okay, so we have in the diminutive form, we got a sine of 2x and a cosine of 2x from the family of derivatives. And so we can set up a particular solution. And so adopting what we have from the group of elements, namely the term and the derivatives, we can say we have a sine of 2x plus b times the cosine of 2x. So this is our general solution set up, and we're looking at solving for a and b. And to get things set up along the lines of y prime equal to 3 times the sine of 2x, I want to take the first order derivative of y sub p. So in this case, a sine of 2x, this will go to 2a cosine of 2x. And for b cosine of 2x, the derivative will go to negative 2b times the sine of 2x. And again, taking for what we have with y prime, and if I put this in the framework of where I have that set up for y sub p prime, so I can say that I have y sub p prime is equal to 3 times the sine of 2x. And so we have this coexistence of expressions that will define the first order derivative of y sub p. And so if I set these expressions equal to each other, so we have 2a cosine of 2x minus 2b times the sine of 2x is equal to 3 times the sine of 2x. And I'm going to duplicate this equation. And if you notice on the left and right hand sides, we got sine of 2x terms, but we don't have a cosine of 2x term. Okay, so you can say that we have 0 cosine of 2x. And if you notice, okay, you have 2a cosine of 2x, but we don't have a cosine of 2x term on the right. So we can say that we have 2a is equal to 0, and right away we have that a is equal to 0. However, with the sine of 2x terms, we got negative 2b sine of 2x equal to 3 sine of 2x. And we can just set the coefficients equal to each other. So we can say that we have negative 2b is equal to 3. And we have that b is equal to negative 3 halves. And going back to our particular equation, okay, notice I had said that a excuse me, a was equal to 0, and b we have at negative 3 halves. And transferring back, so we're going to have for the particular solution, we have that y sub p is going to be equal to negative 3 halves of the cosine of 2x. And we're going to have just in its entirety, okay, for y sub x. That's just going to be the sum of the particular and the complementary solutions. So this will come out to negative 3 halves of the cosine of 2x plus the constant. All right, now let's say where we might have what is referred to as a duplication. And we'll say that if we're looking at solving for y, whereupon we have that y prime is equal to, and we'll say that we have the, 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 and we the sine of 4x, and we'll say that we have plus 3x squared. Okay, and again, because we have just a first order differential equation, again we have that the complementary solution is just going to be a constant. And if we look at each of the terms on the right hand side of the equation, okay, so you got the sine of 4x, and again, just within the family of derivatives, you got the sine of 4x, and the derivative of this is going to be a multiple of the cosine of 4x, and which is going to, once you take the derivative you have going back to a multiple of the sine of 4x. Okay, so this is what we have for the family of derivatives from the sine of 4x term. And in the case of what we have from 3x squared, okay, if you notice we have with 3x squared, okay, this is going to be in the family of x to the n, which you're going to have going down all the way to a constant. So for 3x squared, okay, so you have the variable factor, we have x squared. The derivative of x squared goes to 2x, but in diminutive terms, not worrying about the multiple, we have x. Derivative of x goes to a constant. 1 is going to be a constant. And if you notice from this, okay, sine of 4x, you got sine of 4x, cosine of 4x, there's no constant. But if you notice with 3x squared, we have x squared, x, and guess what? We've got a constant this time around. And then we have what's going to be referred to as a duplication. Duplication of a constant. And what's going to happen here is that to make amends, okay, you're going to multiply everything that's in this family by x to remove the duplication. So what's going to happen here is that what was x squared becomes x cubed. What was x becomes x squared. And what was the constant? Okay, we're going to have at x. Okay, so looking at what we have with y sub p. Okay, we can set up some terms here. Now, we have initially, okay, so if we look at combining what we have here, so we got sine of 4x cosine of 4x, and you got with 3x squared, we can take what's referred to as the union with x cubed, x squared, and x. And if I take the union of sets, we have the sine of 4x, the cosine of 4x, x cubed, x squared, and x. And establishing coefficients, we see we have y sub p, we have a sine of 4x plus b cosine of 4x. Then we have from x cubed, x squared, and x. I'll say that I have plus cx cubed plus dx squared plus ex. Okay, now I got the equation in the form of y prime. So I'm going to do here, I'm just going to take y sub p prime. So if I take the first order derivative, so I have 4a cosine of 4x minus 4b sine of 4x and for cx cubed, we have 3cx squared plus 2dx plus e. And just taking what I have from the original equation and just setting y prime to y sub p prime. So I have this set of terms, and if I set these expressions equal to each other, okay, so if you notice in mapping together, okay, you got sine of 4x and negative 4b sine of 4x. So just kind of drawing some of the equivalents here. Okay, so you got like negative 4b sine of 4x on the left, 1 sine of 4x on the right. So you got negative 4b is equal to 1. So b comes out to negative 1/4. And if you notice, we have 3c times x squared on the left, 3x squared on the right. So we can set 3c equal to 3, whereupon we have c is equal to 1. And if you notice, we don't have a cosine of 4x term on the right, so a goes to 0. We don't have a first order x term on the right, so d goes to 0. And we don't have a constant on the right, so e is going to go to 0. And in terms of what to do with the values of b and c, and if we go back to what we had in the y sub p setup, okay, so again, a goes to 0, as will d and e. And b we have at, again, we have at minus 1/4. And c we have at 1. And so relaying back, and it's going to turn out that for y sub p of x, we end up with negative 1/4 of the cosine of 4x plus x cubed. And since the complementary solution is just the constant, well, we're going to have for the whole solution, we're looking at negative 1/4 of the cosine of 4x plus x cubed followed by the constant of 1. Okay. So just kind of backtracking, and if you notice with our original equations, we had y prime is equal to the sine of 4x plus 3x squared, and guess what? The integral of this expression brings us to what we have for y of x. And for the problem we had prior, okay, notice we had y prime is equal to the expression. We had 3 sine of 2x dx. And guess what? The antiderivative turns out to be what we had with the entire solution for y of x. And for what we started out with y prime equal to e to the x, of course you're going to have e to the x dx is going to have the antiderivative e to the x, and we have followed by the constant. So With what I have had here, this is what's referred to as the method of undetermined coefficients, and especially for the first order non-homogeneous differential equations, you could kind of frame it as, in some contexts, as an alternative to utilizing what is referred to as integrating by parts.